So let's go ahead and start today's lecture. So before I cover today's lecture, let's just do a quick recap once again of what we've done for the past 2 days. So there were two pretty much main theorems that we talked about. The first one being the power rule. We know if I take a derivative of x to a power, or to n power, the derivative of that expression is n times x to the n minus 1. Or we use the phrase break down the power, reduce the power. And then we also had the other one, which was the derivative of e to the x, which was still e to the x. So those were the two rules that we've talked about already. So unfortunately, one thing is that even though those rules were really useful, they're still very limited. Again, power rule, I can only deal with x to the n power. Maybe I can have a coefficient in front, that's fine. And then e to the x is stuck to e to the x. What if, for example, I had a function like x cubed times e to the x, taking the derivative of something like that. When I look at something like that, x cubed e to the x, I can't do power rule. It's not just a plain x power. I can either use, it is true that the power rule and the derivative of the exponential function, which is x, those will come into play. But in its current form, there's not much we can work with. So hence, as you can imagine, this is a product of two functions. We learned how to find its derivative using the product rule. And we're also going to do something similar with the quotient rule, using similar ideas. So we're going to go ahead and jump straight into introducing the product rule. How do I take the derivative of a product function? So our first theorem for today. Suppose I have two functions. We're going to generically call it f. Let's say I want the derivative of that product. So again, remember d dx, and this is derivative of, in this case, f times g. I'm going to show you right here. I have a very formal definition of polynomial notation, and then you're going to hear me use a phrase that you're going to hear me actually more often use it through the semester. So the derivative of f times g turns out to be f times g prime plus g. So if you wanted, you could use this formula, we'll call it. Again, the derivative of f times g is f times the derivative of the other, plus g times the derivative of the other. But you're not going to really hear me often say f g prime plus g f prime. Rather, the phrase that you're going to hear me say a lot is, if I have a product, let's call it f, let's call it the first, and then g, let's call it the second. First function, second function, and a product. So the derivative of the product, I'm going to list it as the first times the derivative of the second plus the second derivative of the first. So if I want the derivative of the product, you're often going to hear me say first, the second, First function times the second plus the second function derivative of the first. So this is our product rule. And actually, this vastly expands types of functions. For example, you take the derivative of what I wrote there on the board, x cubed equals x. So I did go some time to copy down this product rule. Again, whatever it is to your preference, at g prime, prime, second. Note that it is going to be a plus in the middle, but it's possible that one of my derivatives has a negative term. That makes sense. So we're going to do a couple of examples involving the product rule. All right, so let's go ahead to the next. Example 1. Find the derivative of the following functions. So here I have part A, and I'm going to show you two ways that I could have taken this on. So for part A, I've got f of x is equal to 4x cubed times, in parentheses, 6x squared minus 5. So I have that. So let's go ahead and start with trying to see if I can apply my new product rule. So if I look at f, is this a product of two different functions? In other words, is this one thing times another? Yeah, for sure. I have 4x cubed times my other expression, for example. So I can definitely identify this as a product. So I'm going to use that letter as the first and second. I'm going to underline my first, 4x cubed. And then do the same thing for another part. And again, I'll mention that if you prefer an FT prime, that type of notation, that's perfectly fine. So, according to my product rule, the derivative of this product is the first. So it's copied down this expression. 4x times the derivative of the second. Let's write that down, be second. What's the derivative of my second expression? Yeah, derivative of 6x squared. We have power rule, which allows us to bring down the power. Giving me 12x. Derivative of -5, that's a constant, which is 0. And then I take the derivative. So at first, be second. Plus, we have second, be first. So second, I have quite literally copied down the second expression. 6x squared minus 5. I did the derivative of the first. What do I get? Yeah, I get 12x squared. So we just found the derivative of this function. And yet I could clean this up more if I wanted to. For example, you can multiply 4x cubed and 12x and then distribute 12x squared. But for our class, I want to say that this is sufficient for us, is leaving it in this form. Yes, I know it's not simplified all the way, but for our course, we're going to leave it. There will be cases where I ask you to simplify it. So we have our derivative. So a quick question I want to ask is, if I did not have the product rule, I'm going to say that it would still be possible for us to find the derivative of this function using only the power rule. How could I possibly avoid using the product rule here? Yeah, so if I look at this original problem, that's a product, but I could clean that up before I take the derivative, right? I can distribute that 4x cubed. For example, if I distribute the 4x cubed, 4x cubed times 6x squared, I get what, 24x to the fifth power, and then 4x cubed times -5, I get -20x. And then I could take the derivative of that using only with the power rule. So if this is true that I was able to multiply this out and then just use the power rule, then what's the point of really having a product here? Why might a product rule that necessary for us? Right? In this case, it wasn't technically necessary, but when would a product rule be required? Yeah, for example, something like that, x cubed e to the x. There's no way I can rewrite that to just use power rule only. In that case, I would have to use a product rule. The reason why here I was able to reduce it down to just using a power rule is that I had a polynomial times a polynomial. But we know that there can be more complicated. All right, so again, this is our solution that I will be taking. If you want to simplify it, by all means, you're more than welcome to clean that up, multiply it together. But as you will see, especially whenever we start working on the chain rule later on, it's going to very quickly become a huge mess if we try to multiply. All right, so any questions about this part A example? All right, so let's go ahead and move on from here. Let's work on this one. H of t is equal to t minus 3 times 3 squared of t plus 3. So before I take the derivative, one thing that's a pretty common thing that we'll end up doing is that anytime I see a square root, I'm going to convert it to its exponent form. Because I know that I can't really take the derivative of the square root whenever it's in its radical form. So I'm going to go ahead and rewrite this slightly, not by much. T minus 3 times 3t to the 1/2 power. So again, I just changed that radical into a fraction. I don't know one way or another. Sooner or later, I'm going to have to change that. Now let's go ahead and get the derivative of h of t. That is, let's get h prime of t. So I think here it's very clear that we have a product in my function. I have one thing times another expression. If you want, you can just label these as, for example, actually go ahead and use 2 different colors and write this in the other color. Let's do t to the 1/2 plus. All right, so let's go ahead and say that t minus 3, let's call that my first. And let's call 3t to the 1/2 as my second. So let's go ahead and apply our product. What's the first thing I'm going to write down? T minus 3, which then is my first. Next is my d second. Again, all according to product rule. What's the derivative of the second? Yeah. We can say 1/2 or more accurately as an improper fraction, 3/2. T to the, what's the power of the t here? Yeah, -1/2. Because we're just subtracting 1 from the power. It's the power rule. And the derivative of 3, we get 0. So I have first the second plus the second, which again we just copy down plus 3. And then times the first. What's the derivative of the first? Yeah, we have a plain nice one. Here I'm just writing for notes, but usually I wouldn't bother writing times 1. All right, so we found a derivative. And once again, I'm going to tell you all that. I'm going to let y'all leave it in this unsimplified form. Maybe you can leave out the times 1, because that's not really changing it. So we have product rule. That's why once again. And I'll mention, yes, I could multiply it out. This one would not be too bad for us to multiply out. We just have to be careful. Any questions about this part B? I believe I have a part C that I'll give you a couple minutes to work on using the same concept. Look at something like this. I'll start y'all off and then I'll have you all finish. So here I have K of theta. If you're not familiar with the symbol, this is a theta symbol. Often used for angles, but in the end, it's just a Greek letter variable. Let's say I have theta squared minus 2 theta minus 1. All of that squared. So looking at this, it doesn't look like a product. But I claim we can still use the product. Why can I possibly say that? It's a square. And a square is just saying, I take that expression times itself. In other words, what I can do is I could write this technically as theta squared minus 2 theta times the same thing. That's still the exact same expression. Hence, from there, I can go ahead and apply my product rule, where I have my first and my second. So go ahead and see if you can figure out the derivative of this using the product rule. While you want to give that, I'm going to go ahead and write it up on the board myself. And it's unsimplified form. You're probably getting something that's like. Again, we could simplify this, but that's not going to be considered. Primarily because I want you to focus on your product rule itself, rather than all the algebra that comes after. As you can imagine, if I did ask y'all to multiply this out, it might be a little bit tedious if you have a trinomial times binomial. You'd have a lot of distributing going on, but still within the realm of doable with some tedious. So that is example 1, part 2. Again, all it is write down the first. The derivative of the second was 2 theta minus 2. And I'm typically going to be expecting the exact same expression. The second and the first are still the same. All right, so we have our product. I'll give y'all just another couple of seconds to copy down anything as needed. One thing I do want to mention as well for the product rule. So far, we've been doing the product of two functions. You can imagine that really, if I wanted to, I could do the product of three functions, four functions if I want. Which leads us to the idea where if I really wanted to get on an example, have a product rule within a product rule. We're going to see some examples through this semester. So let's go ahead and clear this up. Let's do an example like what I had on the board. Example 2. Let's say I got g of x is equal to x e to the x. And then I want the derivative to start us off. So I'm expecting this one to be a little bit of a quick one for part A. So if I had x times e to x, what can I label as my first? What can I label as my second? So third one first. Yeah, I can probably just use x as my first. And that leaves the remainder e to the x as my second. So the derivative g prime of x. Once again, all I'm doing is following through with my product rule, which we know is first d second plus second d first. So the first x, what's the derivative of my second again? Direct first d second plus the second e to the x. And what's the derivative of the first? 1. And I'm not going to bother writing times 1 because that doesn't really change anything. Great. We found this derivative. For practice, let's go ahead and find the second derivative. Let's get g double. So there's two ways that people might be doing to get the second derivative. So if I want the second derivative, I need to get the derivative of the first derivative. So going down the line, I need the derivative of this one. How can I possibly speed up my process? I could do product rule again. But do I really need to do product rule necessarily again? No, because I already got this derivative, right? I already know the derivative of x e to x. This is the whole thing. So the derivative of this right here, we know that's x plus e to x. Plus, what's the derivative of, I guess, e to x? We still got e to x. So I'll pause here in a moment. This came from the derivative of this expression. And you're saying, well, we already found that derivative, we're going to do product rule over again. This e to the x came from a derivative of e to the x. So this is one of the times where I'm going to say, let's see what happens whenever we simplify. Really, all I can do here is say, I got x e to x plus 2 e to the x. Because these are both e to the x's, I can combine them. Let's get the third derivative. So third derivative, I'm using this So I'm looking at this expression. So once again, we're probably noticing a pattern here. To get the third derivative, I need to take the derivative of what I have here. Derivative of x e to the x. Again, we know what that is. That was up here. So I have, again, x e to the x plus e to the x. That came from this. What's the derivative of 2 e to the x? 2 e to the x. And how could I clean this up just a touch more? I get x e to the x plus 3. Am I noticing a pattern here from the first one to the second? You should be noticing a little bit of a pattern. Enough where if I told you to find the fourth derivative, you probably guess what it is. Plus 4 e to the x. That's for the fifth derivative of x e to the x plus 5 e to the x. So if I were to generalize this, I can say the nth derivative based on what y'all told me was x e to the x plus n e to the x. So if I went the fifth derivative, it would be 5 e to the x. If I went the 20th derivative, you'd get 20 e to the x down there. So this was actually going to be the part B, getting an expression for the nth derivative. And unfortunately, we won't always be able to get something nice like this to get a general expression for the nth derivative. Sometimes that derivative, it may get larger and larger, or it might get smaller and smaller after a while. But in this case, we had a little bit of a nice pattern going on. Any questions about how we finish this example? Right, so I'm going to clear this up. Like I said, part B was me asking what's the nth derivative. That expression I included here. So we've actually already completed part B while we were at it. All right, so lots of nice things that we can do with product rule. Let's see what we have next on here. The quotient rule. So let's say I have a quotient f divided by g. Then the derivative of a quotient using f and g is gf prime minus fg prime over g squared. As you can imagine, it's going to be like the product rule earlier, where I gave you all the formal f and g notation, and then we're going to have an expression for it. So I'll give you all some time to copy this down first before I give you the example. And if you happen to have taken a calculus class before or taken a control account, I've heard this phrase. And just like the product rule, you could use the f and g's or this phrase. I also know that since these are theorems, these are things that have been proven. Technically, if we wanted to use that limit definition all the way back from last week, we could have used them right here, I believe. All right, so let's go ahead and talk about how else might be the quotient rule. Remember, quotient refers to essentially whatever I'm doing. So a lot of times, we're going to hear me say it's f and g. You're going to hear me call the top be the high, and then the bottom to be the low. High is in the top expression, low as the bottom expression. So a lot of teachers and professors often use the phrase that the derivative of a quotient or the quotient rule is low to high minus the high low all over low squared. Same idea as before whenever we had first and second. D high is the derivative of that top expression. So after the exam, where we get back to this concept, you're going to hear me constantly say, all right, quotient rule, tell me what it is. And then you'll go low D high minus high D low all over low. One thing to be careful about, common mistake I see, that remember for quotient rule, the formula has a minus in the middle. The product rule before had a plus in the middle. Make sure that you don't get your plus or minus mixed up, because obviously that means that your final answer will be off by a positive or a negative. All right, so we have our great quotient rule. And with that quotient rule, now we can do the derivative of quotient, and we can also do derivative of products. And actually later on, whenever we cover the chain rule, and the later section might be next week or the week after, you're going to find out that the quotient rule and the product rule, technically they're actually the same formula in the long run, depending on how you look at it. So let's go ahead and just do some quick examples where we apply the quotient rule. Example 3. Find the derivative of the following functions. This time I've got g of x is equal to the quotient 5x squared plus x minus 3 over x cubed minus 3. So once again, I clearly have a quotient. I have something that looks like, well, a fraction. So the way I'm going to end up approaching this is just like the product rule. Remember, for product rule, I said let's identify the first and the second. Well, for quotient rule, I'm going to identify the low and the high. And sort of fortunately for the quotient rule tends to be a little bit more obvious about what's high and low, because I'm quite literally asking what's the denominator, what's the numerator for low and high, respectively. So if I look at this expression, the high is always the numerator. Right, this is the high. And then the low is whatever the denominator is. So if I want the derivative g prime of x, then I just follow my quotient rule, which states that the derivative of a quotient is the low, or in this case, x cubed minus 3, times the derivative of, where's my d high? Yeah, 10x plus 1, again, just applying our power rule. So I have low d high minus the high, which means we just copy that down again, times the derivative of the low, which is what? And we have 3x squared all over big line low squared. So the bottom low was x cubed minus 3 outside of parentheses. We have our derivative. And this is a moment where you can see why I don't really want y'all to be trying to simplify this down, multiply it out. Can y'all do it? Yeah, I'm sure y'all could. Do y'all probably want to do it? I'm going to guess no. Trying to simplify it. higher than is our solution. Unsimplified, granted, but it's our solution. Any questions about how we just apply the quotient rule? As you can see, it can get very long very quickly. I think, for example, I think there was one example I did a couple of years ago where I ran out of board space on like a projector like this. So I just started writing on the whiteboard just because it looked a little bit longer than what I had here. All right, so let me go ahead and clear this one up as well and move on. Let's go ahead and just talk about it. So I have 6z minus 1 times 3z minus 3 to the negative 1 power. So in its current state, and how this problem looked, we can't find the derivative in its current state. Why can't I get the derivative? What was that? Yeah, so if I look at this, we know how to deal with a product, we know how to deal with a quotient, but we haven't done anything about what about something to like a power like that. But I could rewrite this. What does it mean whenever I have a negative 1 power again? Yeah, it basically means I can throw it to the bottom. So if I want, I could write this as 6z minus 1 all over 3. All of a sudden, I got a quotient. I can apply my quotient rule. So the derivative k prime of t. Now tell me, what should I write down? 3z minus 3. What's next? Yeah, we have a times 6, the derivative of I, minus 6z minus 4. Yeah, we got 6z minus 1, because that low behind minus that I. Yeah, times 3 below all over low squared. 3z minus 3 squared. And all of a sudden we are done. I found the derivative. Again, granted it's unsimplified, but the derivative is a derivative. What was that? Yeah. We're going to see, right now we're dealing with primarily polynomials and each to x. Later on, we're going to be focusing on what happens whenever I start adding trig in there, like sines and cosines, and then inverse cosines, inverse sines. What happens whenever I deal with more complicated functions. All right, so this was part B of example 3. So what I'm going to do is I'm going to just show you an example of a problem we'll do in the future. We're not actually going to work on it. Just a preview for what's happening in the next couple of sections. So again, this product and quotient looks nice, but again, it's still very limited. Later on, we're going to talk about, for example, okay, we're not going to actually work on this yet. We were able to work on x minus 1. We did something like that. Not a big deal. But what if I had something that's squared? We had to get 38 power. Good news is that I'm clearly not going to be using product rule on that later. That would mean I have to use product rule 38 times. What we're going to learn a little bit later on is this thing called chain rule, which is, without going too much into depth about it, I'm going to start off by introducing a generalized power rule for any expression. And in the end, this sort of looks like t to the 38 power, right? Something to the 38. We're going to find out later that we're still going to use the power rule, but have it slightly generalized so that we can work on stuff like this. Clearly, I don't want y'all to multiply this all out 38 times. That would just be tedious, maybe if someone like that could. But we're going to be learning rules on how to deal with stuff like that. Later, we're going to deal with how do I deal with something like that, for example, where I start at this point, it kind of looks like I'm starting to make up some functions, which partially will be true. Some of these functions I will be making. So this is sine of e to the cosine of x power. All right, so that's all for today. There are still some stuff about product and quotient rule that we will cover. But I think what's going to happen is that we'll cut it off for today, Thursday, and Monday we're going to do review, and then Tuesday is our exam. So this is a good spot to cut off because that leaves me time to review whenever we finish the exam later on. So this is the cutoff for content for right before we start doing it. Also, as a reminder, this stuff is not on exam one. Everything from power rule, basically what we did this week, is not on the first exam. They went everything up to the limit